Hi everybody, this video here will focus on the process of how you convert polar coordinates to rectangular coordinates and vice versa a little bit, okay? So we're going to take a look first at an example of how we might use the xy plane to find r and theta from x and y points. So I've plunked in there a little xy point in the first quadrant, and we call that point xy because it is located x distance away from the pole to the right and y units away from the pole above it or upwards. So there's our coordinates xy, and you can see they've kind of formed what you might think of as the sides of a right triangle. Well, we can also attribute to that point a distance directly from the pole. You might call it a Pythagorean distance, which we'll call r. And we can also measure the angle from the x-axis up to that line there. And that's our standard position angle. And so we've got an r and a theta that we can also attribute to that same point. And what we are doing is trying to find a way to use all of these different measurements for that one point to kind of build a bridge from one form of the number to the other form of the number, from polar to rectangular or from rectangular to polar. All right? So we're going to come up with some rules here that help us do that. In the first place, you might notice that, yes, that is a right triangle, and there is a very special relationship between the sides of a right triangle. I kind of alluded to it a little bit earlier. That is, of course, the Pythagorean theorem. R squared equals x squared plus y squared. Well, look at that. We're trying to find r in this case. We already know what x and y are, and we're trying to find r. Look at that equation, how simple that is. In fact, all you have to do to solve it for r is take the square root of the sum of x squared plus y squared. That's it. That's our first little conversion rule for finding the r and theta from x and y. Okay, yes, it's a right triangle. Also, right triangles have some very simple right triangle trigonometric properties. In fact, you can look at that triangle and think that the tangent of theta is y over x. Remember, we have y and x given to us, which turn out to be the opposite and adjacent sides, respectively, of that triangle in regards to theta. And so we'll use those along with the tangent function to find theta. In fact, the theta value for our point is the inverse tangent of y over x. Now, I have to add something in here. This formula that I've just written has a lot of baggage to it, okay? It really only works perfectly well in quadrant 1. It has problems in the rest of the quadrants. All right, if your point is located in quadrant 2 or 3 or 4, this formula doesn't work directly. You can use it, but you have to use a little bit extra knowledge to make it work. All right, so in general, when you use this formula to find the theta value for your point, you must make sure that your theta is valid for the xy quadrant that your point is in. So I've got an extra little bit more expansive warning about this formula here, because when I teach this to students, it often causes almost as many problems as it solves. In fact, you could say that this formula is only correct 1/4 of the time. Unless you also take note of some other things. So here's my warning about that formula. This formula, theta equals the inverse tangent of y over x, must be used with extreme caution. To master this process or this skill of finding theta from a given xy coordinate pair, you must know the unit circle. All right? Remember, we are working mostly in math books. Math books want you to know the unit circle. I want you to know the unit circle. Your math teacher wants you to know the unit circle. So we emphasize using that little device, the unit circle, as much as we possibly can. So many of the problems that you're going to run into will depend on you knowing the unit circle as a shortcut to finding theta in this point. Okay? So to continue, more specifically, what you should know about the unit circle are the tangent values of all the angles all around it. Okay? You should learn all the tangent values of the unit circle. And furthermore, you must acknowledge and take into account that the inverse tangent function has a very limited output range. All right? And that is the source of this problem. The formula that we're talking about is only 100% reliable in quadrant 1. Therefore, my friends, please include the following information along with your formula. Theta equals inverse tangent of y over x in quadrant 1. But in quadrants 2 and 3, you must add pi to whatever your value for the inverse tangent of y over x is. All right? So theta equals pi plus the inverse tangent of y over x in quadrant 2 and in quadrant 3. And then finally, theta equals 2 pi plus the inverse tangent of y over x in quadrant 4. All right? So that formula is kind of tough to use by itself unless you're a savvy trigonometry student. Okay? So bone up on those skills. They're very helpful and will save you a lot of grief. All right, well, let's continue our examples here, and here's what we're going to do here is find x and y from a given r and theta value. All right, so we're going to start with the same diagram there. In this case, we know what r and theta are, and we're going to try to find x and y. Okay, it's a right triangle. We've already established that. And another fact about right triangles is these SOHCAHTOA, or these basic right triangle trigonometric equations, such as the cosine of theta equals x over r. Okay, and I picked that one because we're trying to find x. We know what r is, we know what theta is, we're trying to find x, and we're trying to find y. So here's an equation that relates x and r and theta. And if you just did a tiny little algebraic maneuver on that equation, you would see that x equals r cosine theta. That's one of the rules. That's our next conversion rule for finding x from r and theta. And it doesn't take too much discussion to then say, well, if you want to find y, you're just going to use the sine of that angle, and then more specifically, y equals r times the sine of that angle. And that's from basic algebra and from basic right triangle trigonometry. Okay? So to sum up, we've got these 4 conversion rules here. If you're going from rectangular to polar, you want to know that r value is the square root of x squared plus y squared, and you want to know that theta is the inverse tangent of y over x, but pay attention to the quadrant, please, and be careful and know your unit circle like the back of your hand. If, on the other hand, you're going from polar to rectangular, all right, then you already know r and theta, and you're trying to find x and y, and x is just r times the cosine of theta, and y is just r times the sine theta, and folks, there's our 4 little conversion rules. You got to know these things. You're going to use them over and over and over again. Alrighty, let's do a short example here to finish up. We've got a point -4, 4 root 3 up there in quadrant 2, okay, and so that's x and y. And I know it's unusual to have an irrational number as an x or y coordinate, but your math books, like I say, they want you to know the unit circle, and you'll see why that's in there, and that'll be in probably a lot of your problems, these square root 3 or root 2 or something like that, one of these unit circle type numbers, okay? You'll see why in a second. So there's our coordinates, x and y. We are looking for r and we're looking for theta, and we can use our first little conversion rule there to find r from x and y, x squared plus y squared, and when I put those numbers in there, -4 squared, 4 root 3 squared, that gives me 16 plus 48, that's 64, and the square root of 64 is 8. Aha, there we go. R equals 8. Pretty easy. Let's find theta now. There's theta, inverse tangent of y over x. It is in quadrant 2, so I'm going to have to be a little bit careful about this. I'm actually going to skip over my warning here because, you know what? I know the unit circle pretty well. I don't have to worry too much about this. If I take a look at those numbers, 4 root 3 over -4, that's y over x, in the inverse tangent function, and that simplifies down to the negative square root of 3. So I know that there are 2 places that have a tangent of negative square root of 3. One of them is in quadrant 2, the other one's in quadrant 4, and my point's not in quadrant 4, so I use the quadrant 2 angle, which is 2 pi over 3. So if you know your tangent values around the unit circle, you're going to save yourself a lot of grief in this process, I promise you. So there we go. We did it. We took the point -4, 4 root 3, and converted it to 8, 2 pi thirds. That's the polar coordinates there. All right, well, that's quite a bit, I think, for one video. I hope it was somewhat helpful. Watch it again. Pay heed to my warning of finding theta. It is the trickiest part of this whole business. The rest of it is pretty straightforward. All right, so take care, be well, and go do some math now. Bye-bye.